So that's everything that people had voted on for the week 4 packet. So what I'm going to do now is I'm going to work on the week 5 packet. So this is the molecular orbital stuff. And so for this one right here, right, the A4, what we're going to be doing is drawing out the MO diagram for BN, right? So boron and nitrogen. Now, the thing to think about, right, when you're drawing a heteronuclear diatomic MO diagram is that the location of the s orbitals and the p orbitals of the the energetically wise, right, is going to correlate pretty closely with the electronegativity slash where they are within the periodic table, right? So when the higher, the more electronegative um, an atom is, right, the lower in energy the corresponding orbitals are going to be, and that has to do with the fact, right, that lower in energy, more stable, right? And so putting more electrons onto those atoms is, more energetically favorable. And so when you're drawing a heteronuclear diatomic, diagram, the first thing you always want to do is you want to figure out, okay, well, where is everybody in relation to one another? This pen. Um, right, and so in the case of boron and nitrogen, right, boron is to the left of nitrogen in the periodic table, so we would expect the s and the p orbitals to be relatively higher compared to the nitrogen ones. And so the way that plays itself out, and so wait a second. The pen stopped working again, so the way that plays itself out, right, is that when you're drawing your MO diagrams, you always have one atom on one side, one atom on the other, and then in the middle, right, is where you have then your combined molecular orbitals in that case. And so the way that it plays itself out, right, is that we would expect, if we expect the 2s of the nitrogen to be down here, we would expect the 2s of the boron to be slightly higher. Same thing right here, right, where we would expect then the p orbitals to be right around here, and then the 2p orbitals of the boron we would expect to then again be higher than those two p's. Now, the next thing, right, that you always want to do is you want to make sure at the beginning you put in the amount of electrons that everything has. So boron has 3 electrons, right? So you're going to fill in the 2 s's and then put one into the 2p. In the case of nitrogen, right, it has 5 electrons. So you're going to fill in the 2 s's and then put 1 into each one of the 2p's in those cases. Now, the next thing that you want to do is start thinking about, okay, well, what orbitals are going to be interacting with each other to form molecular orbitals in these cases. Now, it's pretty straightforward and easy for drawing the initial sigma bonding orbital, right? The lowest one, right? So the sigma bonding orbital is always going to be lower in energy than the two orbitals together. So this is going to be a sigma bonding orbital here. And so those are going to be interacting directly. The next thing, right, you're going to have a sigma antibonding orbital that's going to form between the two s's. And so that's going to be roughly right here in that case. So you have that. Now, the next sets, right, the ones that include the 2p's, those can get more tricky because it actually depends very much on where within the periodic table the elements exist as to whether the next set of orbitals are going to be pi orbitals, right, pi bonding orbitals, or whether they're going to be sigma bonding orbitals. And so pretty much a good rule of thumb that you can use is that if you have a heteronuclear diatomic orbital, if one of the atoms is like nitrogen or earlier, right, or like that row of nitrogen and earlier, then what happens is that the next set of orbitals are going to be the pi orbitals in these cases, right? So these are going to be the pi orbitals right here, and then you'll have your sigma bonding orbital in this case, and then after that, right, you're going to have your pi antibonding orbital. You'll have your sigma antibonding orbital up here. Now, the reason, right, why you have that slight change has to do with the fact that energetically, the 2s on the boron and the 2p on the nitrogen are close enough in energy that those can actually interact with each other and form a molecular orbital as well. You know, and so what happens there is that you actually then push and change where the sigma bonding orbitals are, because now they start having different characteristics than being pure sigma or sigma anti-bonding. But I believe that's outside of the scope of this class. If you take Chem 500, right, you'll learn about that there. But that's the reason why that happens, right? But the easiest thing to do is just simply remember, right, in those cases that you have that flip and you have that change. So we have this right here, right? And so then the next thing we want to do now, all of these guys are labeled, is we want to put in the electrons, right? And so we have a total of 8 electrons, right? We have 3 from the boron, 5 from the nitrogen, and so we just fill those in to the molecular orbitals, you know, using the Pauli exclusion principle, Hund's rule, and the Aufbau principle. So right, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, nope. 8 is it. Jumping ahead, right? So we have 8, right? And so that right there then is where all of the electrons reside. And so essentially, right, we have completely filled sigma bonding orbital from the 2 2s's, right? We have a completely filled sigma anti-bonding orbital from the 2 2s's, and then we have 2 completely filled pi orbitals from the 2 p's of boron and nitrogen interacting with each other in those cases. And right, and that's how you construct this MO diagram. Pen works again, which is awesome, right? And so then the next part of the question, right, is, you know, on the basis of your molecular orbital diagram, would you expect the boron nitride cation Bn plus to have a more or less stable Bn interaction? What is the justification for your answer? And so if we go back and look at it, right, we can calculate what the bond order is of, you know, Bn in this case, where we add up the number of electrons in the bonding orbitals, right? So to calculate, here, let me switch, right? To calculate bond order, right? It's the number of electrons in bonding orbitals minus the number of electrons in anti-bonding orbitals. And you divide that by 2. So in this case right here, right, what we had was 1, 2, 3, 4, 5, 6 in the bonding orbitals, right? We have 2 in the sigma, 4 in the pi, minus, right, anti-bonding orbitals, we only have 2 electrons in this case, right? Those are in the sigma anti-bonding, so minus 2 divided by 2. So 6 minus 2 is 4. 4 divided by 2 is equal to 2, right? So we have a bond order of 2 in this case. If we were to do, right, and so this is for Bn. So if we were to think about Bn plus, right, if we were to calculate what the bond order is, why did it stop again? All right. Right, if we were to calculate it now, right, so if we have Bn plus, that means we have 1 less electron. So then in that case, right, what we would have is 5 minus 2 divided by 2. So that would then give us 3 divided by 2, which is then now a bond order of 1/2. And so 1/2, right, is less than 2. And so now we would consider that to probably be a less stable interaction, because the higher the bond order, right, the more stable we would consider a bond interaction to be, right? You know, the interaction between 2 of them, right? Because the higher the bond order, the more energy you have to put in to break that bond. And so, you know, the higher the bond order, again, right, like you would expect that to be more. In the case of Bn minus, right, what happens then in this case is if we go back to the MO diagram and we were to look at it, right, if we were to put in 1 more electron, that 1 extra electron, right, would go into the sigma bonding orbital now. And so we're going to be taking out an electron, or we're going to be putting an electron into the bonding orbitals. And so now when we calculate the bond order, in this case, right, what we have is 7 minus 2 divided by 2, which comes out to being 2.5. And so now, right, the bond order is higher, right? We have a bond order of 2.5. And, you know, it should become more stable interaction between the boron and the nitrogen. But the thing to consider as well is that the higher the bond order, the shorter the bond becomes, right? Because the more the two atoms are essentially getting pulled together, and so we would expect it to be a shorter, BN bond in that case, right? Because you have a higher bond order between the two atoms. And so that's how you do that